Although actually, while we work on that, I was going to make an announcement before the start of lecture. So I'm going to go ahead and do that right now, since we're about at starting time. So thanks everybody for filling out our questionnaires about the quiz. So weighing all the different input and constraints different people have, and in particular, some of the, extra challenges that working remotely and from home creates for different people. We've decided to go with no proctoring, so just honor system relying on your honor and general MIT honor code. It seemed to be the most pragmatic trade-off that we can make this time around. So you don't need to be keeping yourself live on Zoom on your Zoom camera or anything during the quiz next Thursday.
Angelina Lee is a professor at Washington University in St. Louis. She is the author of the Open Cilk runtime, which is based on her research runtime system called Cheetah. And she's also the runtime architect for Open Cilk. So she intimately knows, how to do scheduling and how the runtime system and language interact. She's a, probably world's expert on language runtime systems for task parallel languages. There's only one other person I would sort of put in her category, and that's Umut Akar at Carnegie Mellon University. But the two of them are sort of like, I would say, are pretty much the top people in language runtime systems and the mechanisms and so forth. How do you make it so that it's easy to work? And today we're going to find out about the different mechanisms that are in there, how work stealing works, why you randomize, and I think you're going to find it really very interesting. The Open Cilk runtime system is about, we can ask her what it is, but it's just a few thousand lines of code, and which is really pretty amazing, that you can do as much as she does in just a few thousand lines of code. It's about a quarter the size of Intel's runtime system, which is what we have been using up to this point, until this year. So it's really much smaller runtime system, much easier to modify, much easier to improve, I hope, because one of the things I've learned about software is the smaller it is, the easier it is to modify and to get better performance from and to support new features. I hope one of the TAs is looking for when Angelina gets on board and can host her as quickly as possible. And so we can get going when she comes. I was looking through some of the status reports, and I think there's some really good feedback there. I really appreciate people's thoughtfulness in the comments that we're getting. There are, we're good comments on a variety of issues, and one of the things, of course, is everybody wants. A couple of people mentioned, "Gee, I'd like to get more individual feedback on my projects." And this is one of the things where, like, there's so many more of you folks than there are of us. And so we got to figure out how we can batch. This is one reason I think the MIT Posse works well. But it's just one of these things that unless, the best way to do that, frankly, is become a UROP or an MN student with Jonathan or me. Okay, because when you're UROPing, that's where you get lots of individual attention from the professors and also from their graduate students. You end up operating as ideally as a colleague, even if you're not the senior person on the project, you generally will have a project of your own. So let me just encourage everybody to, I'm sorry, I would love if you have ideas of how we can leverage the limited staff that we have to, minister more individual attention. I'd love to hear it. We have office hours. Maybe we should have post-mortem office hours. And I think there's no reason you can't use that. There's an issue of, how does somebody come up to speed with, quickly with your entire project in that amount of time. I see Angelina has joined us. Okay, Professor Lee.
Hello. I am terribly sorry about the time mix-up. Really sorry.
Not a problem. I've already introduced you. I've said a lot of things that would probably make your ears turn red.
Okay, I'm glad I'm not there for it.
But we're recording, so you will have every opportunity to look back and make trouble for me in the future.
Okay.
So with that, let me turn things over to you.
Okay, great, thank you. And I will say, if anybody posts, I welcome question, and if anybody posts question, I think I communicate this to Helen. Can somebody just bring my attention to the Slack chat, because I may not always notice.
Yeah, I usually put the Slack chat on my phone.
Which we can try to raise.
Oh, we can help. Yeah.
Yeah, we can help.
We can help.
Yeah, sorry. Originally had set up in my office, and because of time mess up, my husband is actually also giving a lecture in the study, which is supposedly where my setup is, and
no problem. We'll try to make sure you can handle questions more easily.
Thank you. Okay, so let me pull up my slides. All right, I need to share. Okay, can people see the PowerPoint slides?
Looks good.
Okay, all right. All right, hello everybody. Today I'm here to tell you a little bit about a work ceiling runtime system. Okay, so let's see. So I think at this point you are familiar with the Cilk programming language, right? We see how you can basically annotate the program using spawn and sync, where a spawn basically indicates that the function that you're invoking can be executed, potentially be executed in parallel with the continuation of its parent, and the sync is the counterpart that states that all the spawn subroutine has to terminate before the control can pass sync. Now, when this piece of code, which I'm showing you the parallel fib, when you schedule this on the Cilk platform, basically what happens is that there's an underlying Cilk scheduler that maps the executing program onto the available processing core dynamically at runtime, right? So what that means is that when you say Cilk spawn fib n-1, it doesn't necessarily mean that fib n-1 is executing in parallel with the continuation of the parent. In this case, fib n-2, it may or may not, depending on whether there's available processing core at the moment. And the whole computation is executed using what we call a work ceiling scheduler. And the work ceiling scheduler is provably efficient. And today I'm basically going to dive a little bit into detail on how this scheduler is implemented. Okay, and I think you have seen this picture in prior lectures, but basically the work ceiling scheduler is basically implemented using a combination of a compiler and runtime library together. And so it's really a collaboration between the runtime and the compiler. And today I'm going to focus a bit more on the runtime part. However, the compiler actually also play an important part, which I will touch on later. Okay, but before I dive into the implementation detail, I will give you a high-level overview of what work ceiling is about. And I'm going to talk about a really important principle called the work first principle, which is basically how we organize the runtime system. And then I'm going to talk a little bit about the required functionality of the entire platform, and then dive a bit more into detail on the various data structure organization in the runtime system and how we implement the required functionalities. And then I'm going to end on a discussion on various design choices that we made in the runtime system. Okay, so at a high level, right, when you have a work ceiling system, what happens is that when the parallel computation gets started, the platform spawns of multiple key threads or a persistent thread, where the number of threads that you have managed by the runtime system basically is equivalent to the number of cores you have on the system. And each such worker, which you can basically think of them as a surrogate of processing core, maintains a work deck of ready strands. And it basically manipulates the bottom of the deck like a stack. And so what do I mean by that? Well, for example, if a processor executes a function call, that call frame gets pushed onto its own deck because now that worker is in some sense responsible for executing that computation. Similarly, if a worker spawns a subroutine, that also gets pushed onto the bottom of the deck. And then notice that all the worker can operate independently on its own local deck. Now, when a worker runs out of work, it basically randomly chooses a victim and steal from the top of the victim's deck, okay? So here, one thing I will mention, notice that earlier when I pushed the frame onto the bottom of the deck, I always use spawn to indicate if a function were spawned, and I use call to indicate that particular function frame has been called. So in this case, when worker 2 steals from worker 3, it actually steals 2 frames. Does anybody want to take a guess as to why we're stealing 2 frames from the top instead of just 1 or instead of many? So I guess in this case, I think people are muted, right?
They're muted, but they usually respond to open-ended questions by typing in Slack.
Gotcha.
And it seems people are typing. Can you see the Slack?
Yeah, I can.
Okay, good.
Good. Okay, so great. We already have a few responses, and I think people sort of gather, right? In this case, so good. People are sort of getting the right intuition. In this case, notice, right, on the third worker, where previously the top 2 frame has spawned and then called and spawned. And in this case, the second frame that's stolen by the worker 2 has previously spawned, right? Just judging based on what's left on worker 3's top of the deck right now. And this is why we're stealing the top 2 frame. Because in Cilk, recall that when you spawn a subroutine, the continuation of the parent can potentially execute in parallel. However, that's only true for a subroutine that is spawned, but not for a subroutine that has been called, right? So in this case, the very first frame stolen by worker 2 has just previously called, and only the second frame has previously spawned. And so when worker 2 resume the stolen work, it has to resume basically after a function that has been spawned. And so in this case, it has to steal the top 2 frames together because those are basically a unit together. The first frame actually cannot be resumed execution until the second frame return. And that's why we're stealing 2. Okay. Now, so as I mentioned earlier, a work stealing runtime actually provides provably efficient execution time. Okay, so let's take a look at that. Here, I'm going to use the notation TS to denote the work of a serial program. So with Cilk code, right, for any parallel code, you can basically omit the spawn and sync and convert a Cilk 4 into a regular 4, then you get a corresponding serial program. And so we call that program the serialization. So let TS denote the total amount of time it takes to execute that particular serial piece of code. And then we're going to call T1 the total time or the work to execute the corresponding parallel program. And T infinity or the span, T infinity on the other hand basically denote the span of the parallel program. And typically, right, when we measure the execution time running the parallel code on a P processor, we measure how much parallel speed up that particular code gets on P processor by taking TS divided by TP. Okay. Now, in terms of work stealing scheduler, it's been shown that it achieves the following expected running time. Okay, again, TP denotes the execution time running on P processor. So theoretically, we can show that the time it takes to execute the parallel program on P processor is equal to the total work divided by P, where P is the number of processor you're using, plus big O of T infinity, the span. Okay. Now, this span is actually pretty good, but let me just give you a bit of an intuition. Earlier I mentioned, right, in the work stealing runtime, a worker is either working, and in which case it's mostly operating on its own local deck. However, when it runs out of work, it turns into a thief and tries to steal from a randomly chosen victim. And so, in a gist, a worker during execution is either doing useful work or it's trying to steal to find work to do. And so the first term, you can think of it as roughly spent, corresponds to the time workers spend working. On the other hand, the T infinity term, roughly speaking, you can think of it as the time workers spend doing steal. And in particular, actually, the overhead in front of the span term that is currently hidden in the big O notation, roughly corresponding to the overhead of a steal. Okay. And I'm kind of hand waving a bit because, I didn't want to get into too much technical detail on the theory part. Now, the thing to know about this bound is that if the program itself has ample parallelism, and where the parallelism, which is defined by the work divided by span, if the work divided by span is much greater than P, the number of processor you use, then notice that the first term, the work divided by P, dominates. And so in this case, assuming your application has an ample parallelism, the scheduler actually likely to achieve linear speed up because, again, TP will be roughly equal to T1 divided by P. Okay. Now, coming back to the parallel speed up, earlier we mentioned we want to measure the parallel speed up by taking TS divided by TP, right? And so in order to achieve linear speed up on P processor over the serialization of the parallel code, meaning we want to get TP roughly equal to TS divided by TP, then the parallel program must exhibit two properties. The first one is, as was mentioned, it should have ample parallelism because that's how the scheduling bound has the first term dominate, and therefore getting TP roughly equal to T1 over P. But then the other important thing is that it should have high work efficiency, meaning that when you execute the corresponding parallel code on one processor, its execution time should be close to whatever execution time you have executing the serial code. Okay, so these two criteria must be met in order to achieve linear speed up. So based on that, the runtime is organized what we call the work first principle. Okay, to optimize, and the work first principle is designed to optimize for the execution of a parallel program with sufficient parallelism, where basically we want the platform to maintain high work efficiency by optimize for the ordinary serial execution at the expense of some additional overhead in steals. Because whatever serial execution, the execution time goes into the T1 term, or the T1 over P term in the scheduling bound, whereas the overhead in the steal, roughly speaking, goes into the overhead in front of the T infinity term. And so we really want to optimize for the ordinary serial execution, and even at the expense of putting some additional overhead in the steals. Okay, so before I move on, any questions so far? So, okay, I guess.
There's a question that just came in. How can another process steal from the top of the stack?
Okay. So in the case that I just showed you, it is actually not technically speaking steal from the top of the stack. It's stealing from the top of the deck. And I haven't really get into detail on what is the organization of the deck and what it corresponding to. But roughly you can think of it, the deck as a worker local data, well, not a worker's, a deck is what a worker uses to keep track of all the ready work that it is responsible for, including work that contain potential parallelism in the subcomputation that's available to be stolen. And so in the case of a steal, the thief is stealing from the top of the deck, not top of the stack. Or does that answer your question? And we'll get into a bit more detail on what the deck is all about. Okay, great. Any other questions? Okay, if not, then let's move on. All right. So now, before we dive into the organization of the various runtime data structure, let me just talk a little bit about the required functionality that the runtime system or the platform overall needs to support. Okay. So I believe you have also seen this picture where assume you're executing a parallel fib computation, and say you're executing fib of 4, where here I'm color coding the code, right? So each color corresponds to a strand or a sequence of instructions that must execute it on one core, where it doesn't contain any parallel construct. And so when you execute this particular program with input 4, the following trace unfolds, where when you hit the spawn statement, right, you have two outgoing edges, and one goes to the spawn subcomputation and the other one goes to the continuation of the parent, in this case, which corresponds to y equal to fib minus 2, denoted by the blue node. And all the subroutine can potentially have its own nested subcomputation. And furthermore, right, this trace unfolds dynamically as the program executes, okay? So this is conceptually how you think about the execution of a parallel program. But let's see what happens, what can happen when you actually execute this program on multiple cores. So say here, I have one worker currently just executing fib, right? Worker 1 is going to execute the fib just like regular serial execution. And in fact, when you have a single worker executing a piece of code, the worker's behavior mirrors exactly that of the serial execution. Like the order of operation you do is the same as serial execution. And so basically when you hit spawn, in this case, worker 1 will go ahead and execute the spawn subroutine, in this case fib of 3. And note that I'm denoting the input of fib at the top left corner of the box represent the function instance. And so then now it continues to execute fib of 3, which then spawn fib of 2, which then in turn spawns fib of 1. Okay. And say at this point another worker comes in, worker 2, and try to steal. And in this case, say it happens to steal from worker 1. And as we said, it always steals from the top of the deck. In this case, the corresponding deck on worker 1 would be having the function frame of 4, 3, 2, 1, because those are the functions that got spawned by worker 1. Okay, and so say worker 2 happened to steal the function execution of fib of 4. In this case, because worker 1 has already gone ahead and executed the spawning of fib of 3, worker 2 will pick up the execution in the middle of the fib of 4, and picking up the execution exactly at the continuation of the parent after the spawn statement. And then it will continue execution like normal, which means it will go ahead and call fib n minus 2. Okay. And say in this case, another worker comes in and say again, it steals from worker 1, because in this case, the fib of 4 has been stolen by worker 2. Worker 3 is going to then steal the next one down the list, which is fib of 3. Okay. And again, it will resume in the middle of the execution. And notice that, right, at this point, basically, given this particular execution context, each worker basically see the following view of the stack, or you can think of the stack of the function frames that corresponding to what the worker, if you think of the entire spawn tree, right, worker 1 is currently executing fib of 1. And if you think about normal execution, worker 1 would see the stack frame corresponding to fib 1 and all its ancestor up to fib of 4, which means that P1 basically has the view of the stack of fib of 4, 3, 2, and 1. Fib of 2, on the other hand, will have the view of the stack frame fib of 4 and fib of 2. And note that this fib of 2 is a different function instance of the fib of 2 that worker 1 is seeing. And similarly, worker 3 will see the function frame of fib of 4 and fib of 3. And so the Cilk platform itself needs to be able to support such a view of the stack. And furthermore, Cilk support the same rule for pointer for C, meaning that a pointer allocated on the stack can be passed from the parent to child, but not the other way around. And so today, say if someone allocated a stack pointer in fib of 4, that pointer can be passed down to fib of 3 and fib of 2. All the worker would be able to access that pointer allocated on fib of 4. We call such view of stack, which is different from the regular view of a C stack, right? Because notice how P1, P2, P4 simultaneously have the view of fib of 4. And so we call such, they simultaneously have the view of fib of 4. And furthermore, the subroutine of fib of 4, including things like fib 3, fib 2, they are also alive on the stack. And we basically need to support such multiple views of the stack simultaneously in parallel for all the workers. We call such construct as cactus stack. And it's interesting how we support such a view. I will touch a little bit on how we support such a view later, but we won't get into too much detail on it. But if you're interested, I'm happy to answer questions about them later after the lecture. Okay, so now say fib of 3 now reached the point where it needs to execute a Cilk sync in fib of 3. And notice that in this case, worker 1 is still executing on the first spawn child for that particular worker 1 is still executing the spawn fib of 2 spawned by fib of 3, and in fact it's executing fib of 0 that's subsequently called by fib of 2. And so in this case, when worker 3 hits a spawn, it needs to check whether it's ready to sync yet. And it needs to notice that, actually, no, I'm not ready to sync because I have some subroutine spawned by this particular function that is currently executing on a different worker. So in this case, it needs to determine that, no, I cannot actually sync yet, okay? And so in this case, if it's not ready to sync, worker 3 basically has to go away and find something else to do. And the execution of the FIP3 will eventually get resumed whenever worker 1 manages to return from the subroutine. Okay. And so putting everything together, right, there are multiple things that we need. First of all, each worker, we know that it has its own execution context that it needs to keep track of. In particular, it needs to know where it is in the execution. It also needs some stack view corresponding to its current execution. And in particular, its RSP pointer has to be pointing to somewhere in the Cactus stack that's also maintained by the system. Each worker has its own processor state. And each worker also has its own work deck that keeps track of the work item that it is responsible for. Okay, so at a high level, these are the various constructs that we need. And so to recap, right, each worker needs to keep track of its own execution context. And this includes work that it's responsible for, and also work that is potentially available to be stolen by other worker. We need to enable that a worker, after successful steals, to be able to resume the stolen function mid-execution, okay? And then finally, upon a sync, a worker needs to be able to determine whether there's any spawn subroutine that's still executing on another worker. So the runtime data structure is basically sort of organized into the following basic things to support these functionality. First of all, each worker has a work deck that stores the ready execution context. And here I'm using the term execution context. I'm not defining it very clearly, but effectively what you can think of it is, as each worker spawn a function, in order for a thief to be able to resume that particular function upon successful steal, we basically need to know, in some sense, the process state of worker 1 right before the spawn, so that we can resume the function mid-execution, right? And so such processor state is actually stored in a data structure, what we call a Cilk stack frame. Okay, so there is a Cilk stack frame correspond to each Cilk function or a function that can potentially spawn. And the worker deck basically stores references to these Cilk stack frame. And finally, in the runtime, we also have what we call a full frame tree to represent the function instances that has been stolen. So notice in previously when I show you the execution of how the FIP of 4 play out, right? The parallelism, actual parallelism is realized by successful steal. Or put it differently, a function can only have outstanding spawn subroutine executing on a different worker if that function instance has ever been stolen. And so whenever a function has been stolen, we need to keep track of additional bookkeeping information in order to allow the runtime to manage that successfully. And so in this case, beyond the stack frame, which is a more lightweight data structure, the runtime also maintains what we call a full frame, where you basically have a full frame corresponding to each function instance that has been stolen, so that we can maintain the extra bookkeeping to enable the actual parallel execution. Okay. And as I mentioned earlier, right, this is really a collaboration between the compiler and the runtime. And so the compiler, when you compile a piece of Cilk code, it actually generates pseudocode that allow the compiler during execution to manage a handful of data structures. So for example, things like the initialization or any operation on the stack frame or the deck is managed by the compile code. Okay, so in particular, it basically implements the optimized fast pass for execution when no steal occurs. Okay, The runtime library, on the other hand, implement functions that operates on the larger data structure, such as the full frame tree. I apologize, the slices closure tree. I sometimes use closure and full frame interchangeably. And basically, it handles the slow path of the execution when a steal occurs. And we will look into more detail when we talk about the organization of those data structure. But at this point, I'll pause and ask, is there any questions so far?
It's a fast path.
Good. So I will get into it a bit more later, but basically you can think of as earlier, as I mentioned, when a worker execute a Cilk program, for the most part, it mirrors the serial execution, right? And so you can think of the part where it mirrors the serial execution as the fast pass. Now, however, whenever there's a successful steal occur, and then later I will show you a more detailed example, but whenever a successful steal occurs, that's when you have actual parallelization. And in this case, the runtime system has to do additional bookkeeping. And in particular, whenever you hit a sync, you need to potentially invoke more heavyweight synchronization. Or whenever you return from a spawn function, you potentially need to invoke a more heavyweight operation in order to maintain correct execution when there's actual parallelism underneath. And so I am referring to the operation where there's no exit parallelism and you're just mirroring the serial execution as fast pass, and anything involving computation that has actual parallelism where you need to manage in terms of when you're returning from a spawn function or when you execute a sync, those is the slow path. And I will point out more detail on that when we get into the example of how we organize the runtime data structure.
Yeah, let me just say the notion of fast path and slow path is one of the Bentley rules we saw right at the beginning of the class. The idea is you want to optimize for fast paths so that if you are going to be able to short circuit or going to be able to in a branch or whatever, you want to make sure that the fast path stays fast.
Ayush also just asked a question about where new spawns get assigned, whether all new spawns are assigned to the first processor and then get stolen, or are they assigned in some sort of round robin way or something like that?
Okay, good. So notice that here, whenever a worker executes a spawn function, or a spawn call, the worker that executes the spawn actually goes ahead and execute the spawn subroutine. And the continuation of the parent is what gets pushed onto the deck that can potentially be stolen. So in this case, whenever you execute a spawn, the spawn subroutine, in some sense, quote unquote, gets assigned to the processor that executes the spawn. Does that answer your question?
Yeah, so it sounds like they all get assigned to the first one then?
So I'm not totally sure what you mean by assigned to the first one.
So I think the idea is that everything stays on the deck of the processor where they originated and are only redistributed via stealing, not via some other mechanism. Work is never like pushed out somewhere else.
That's correct. And so the way you think about it is just when you execute the spawn, the worker that encountered the spawn statement gets the spawn subroutine. And the continuation of the parent becomes available to be stolen. However, the continuation of the parent can be executed on a different worker, or it can still stay on the original processor depending on whether there's a successful steal that occurs. So if a different worker comes in and happen to steal that function frame, then the continuation of the parent gets stolen, and that's when the continuation of the parent actually gets executed in parallel with the spawn subroutine. And that's what I meant by successful steal is what enables parallelism, like actual true parallelism.
Perfect. Thanks. Yeah, I got it.
Great. Okay. Oh, oops, that's an extra slide. Okay. So now let's look a little bit detail into the various organization of the runtime data structure that I mentioned. Okay. So as I mentioned, each Cilk worker actually maintains a deck of references to Cilk stack frame. Okay, and later on, I will make it more clear what I mean by the references to Cilk stack frame. But basically, the deck manages the work that's available to be stolen. In particular, so let's take a look at an example, right? So say in this case, a worker 1 is currently executing fib of 2. And then it subsequently spawned fib of 1. In this case, it basically, once it spawns, it pushes the Cilk stack frame. So here, what I'm showing you on the cactus stack, you can think of each frame represented by the Cilk stack frame, because earlier, as I mentioned, each Cilk function contains its own corresponding Cilk stack frame. And roughly speaking, for the time being, you can just think of a Cilk stack frame as containing the execution context of the worker at the point when the worker spawned. Okay, and so going back to this example again, say the worker is executing fib of 2, and fib of 2 now spawns fib of 1. In this case, basically, we push the Cilk stack frame for fib of 2 onto the deck, and then the worker then continue executing the spawn subroutine, in this case, corresponding to fib of 1. And so effectively, by doing that, the deck basically keeps track of the ready work that, in some sense, both worker 1 is responsible for, and that is available to be stolen by other workers. Okay. Now, whenever we return from a spawn, what we do is that we basically pop off. So in this case, say worker 1 is about to return from fib of 1 back to its spawn function, which is fib of 2. It tries to pop off the deck so that it pop off the spawn parent of its own deck. And then now the current execution is pointing back to fib of 2. And this assumes that the execution context of fib of 2 hasn't been stolen yet, right? That's how the pop can be successful. If it has been stolen, then it will no longer be in the deck and the pop wouldn't be successful. Okay. Now, so in the case of a steal, right, for the most part, as I mentioned earlier, the worker will operate from the bottom of the deck because the execution basically mirrors exactly of serial execution. When we execute a function, right, it's kind of like a stack where you have first and last out. And so the operation on the deck mirrors that. Whatever that gets pushed onto the deck first comes out last. And the worker basically push and pop stuff off the bottom of the deck. And the thief, on the other hand, always steal work from the top of the deck. And so in this case, the worker always operate at the tail end of the deck, and thief, on the other hand, always operate at the head of the deck. Okay. Now, you do require some coordination so that you are careful to not allow the head and tail to cross, right? And in particular, when the thief and the worker potentially go after the same frame, then you do need some coordination so that one of them gets the frame and the other one fail to do the operation. Either the worker needs to fail to pop or the thief fail to steal. Okay. So how do we do the coordination? Well, in this case, we basically use a mutex associated with a deck that performs synchronization. Okay. And so a naive implementation would be whenever a thief wants to operate on the deck, it grabs the lock. Whenever a worker wants to operate on the deck, it also grabs a lock. However, we can actually do better than that. Okay. In particular, let me just ask the question. Is it more important to optimize the operation of the worker, or is it more important to optimize the operation of the thieves? What do people think? Yeah, okay. Many of you says worker, and right. As we said, as indicated by the work first principle, we do want to optimize the ordinary serial execution path at the expense of putting additional overhead on the steel path. And so in this case, right, worker is just doing useful work, and for the most part, its execution actually mirrors serial execution. If today there's no thief, it would have just popped the thing off and resumed the spawn parent and continue execution. And so in this case, whenever there's coordination necessary between the worker and the thief, we do want to optimize for operation on the workers, okay? And so another thing I want to point it out is that a worker, whenever it's about to return from a spawn function, it needs to pop the stack frame from the tail of the deck. And there are two possible outcomes, right? Either the pop succeeds because the spawn parent has not been stolen, then the execution continues as normal, where the worker would just resume the continuation of the spawn parent. On the other hand, if the parent has been stolen, then the pop can potentially fail, then the worker is run out of work to do, and then in which case it then itself becomes a thief and try to steal. So which case do you think it's more important to optimize? Right, great. Everybody says the success case in the case one. Yes, because why? Probably, well, so actually, given how work stealing works, assuming your application has ample parallelism, likely steal occurs infrequently. And so the more likely case is always the pop is going to succeed, okay? And so in this case, we do want to optimize for case one. So in this case, the runtime actually allowed the worker and the thief to coordinate using what we call the THE protocol. So there are two observations. The first observation is that really the thief and the worker only need to synchronize when the deck is almost empty, right? Because the worker always push and pop by manipulating the tail. The thief, on the other hand, always manipulate the head to take things off the top of the deck. And really the two can only sort of interfere with each other when there's one last frame left on the deck and the head and the tail is about to cross. And that's the only time really you need synchronization, okay? And the second observation is that the pop operation is much more likely to succeed than fail. So in this case, when we use what we call the THE protocol to operate on this deck, what we do is that we basically try to optimize the operation of the worker, where we allow the worker to pop the deck optimistically without grabbing the lock, okay? And then once we decrement the tail, meaning we try to pop, then we now check to see, hey, am I in danger of having my tail and head cross? Meaning, am I potentially going after the same last frame as the thief? And if that's the case, which is if this if statement is successful, then I will put back my tail, and then now I will try to attempt to grab the lock, okay? If it appears that my deck is about to become empty. And then once I successfully acquire the lock, I then try to pop the tail again. And now since I have the lock, I know whatever head and tail value I read is the true current value of the head and tail. And so in this case, either I may potentially fail, in which case I put back the tail on lock and return failure, or maybe I am successful, in which case I get the last frame and I unlock and I return success. On the other hand, the thief always grab the lock. So a thief will, before it operates on the head, it will always grab the lock. And this protocol basically allows the worker to, for the most part, pop its tail without grabbing the lock. and only grab the lock, coordinate with the thief when it's in danger of like having the head and tail to cross. Okay. Sorry, any questions so far about the THE protocol? All right, sorry. Yes, the THE stands for tailhead exception. Exception is a separate pointer pointing into the deck, which I don't touch on in the simplified protocol. Okay. Now, so as I mentioned earlier, right, the worker operates at the bottom of the deck while the thief still works from the top of the deck. Okay. And so say in this case, the thief successfully steal the top of some deck, in this case, the top of the deck corresponding to fib of 3, and worker 2, fib of 4, and worker 2 successfully steal that because they successfully pop it off the head of P1's deck. And now, once they successfully steal, it needs to set up the thief stack in the processor state, right, in order to resume the execution of fib of 4 in the middle of fib of 4. So how does it do that? Well, in this case, this is actually with some help from the compiler to allow us to save and restore the processor state. And in particular, for every Cilk function, there's a local buffer that is allocated in each Cilk frame corresponding to that Cilk function. And so the pseudocode for Cilk spawn roughly translates to the following, where we have the buffer and we basically, the compiler will generate code to save the necessary processor state. This including things like the RIP pointer corresponding to the continuation of the parent, and the various live local variable value that is potentially currently on the register. And I don't know if people are familiar with the set jump call. So set jump long jump is provided by the system library that is actually not specific to Cilk, but rather you can actually use set jump long jump to store away execution context in the middle of a C function, and set jump stores away the processor state, and long jump allow you to resume the stored away processor state to resume the execution in the middle of the function. I won't get into detail on how set jump long jump works, but if you're interested in it's actually a really neat, you should look into it, right? But basically the point is that for every Cilk function, we have such a buffer that allow you to store the processor local state. And we basically use things like set jump to save away the processor state into the buffer. And so the buffer is effectively stored with the Cilk stack frame. And the deck basically has the pointer to such Cilk stack frame. And so that whenever a thief steals from a victim, it basically steals away the Cilk stack context, and now it has this context buffer, and it can resume the execution of the stolen function, basically in the middle. Okay, right. So as I said, basically, you can think of the deck containing references to the Cilk stack frame, which contains this context that I just talked about. As each worker spawn, it will store away the execution context before the spawn, and then subsequently go ahead and execute the spawn function. And the thief, once it steals, it can basically takes the stored away context, and that's how we resume the execution in the middle of the function. Any questions so far? Right. Okay. So now let's talk about the organization of the full frame, right? Recall, whenever we hit a sync, right? If today they are potentially subroutine that's still executing on other workers, then a worker can't successfully execute the sync. In this particular case that I'm showing you, in again the fib4 example, right? Fib3 maybe hit the Cilk sync, And maybe in the previous execution, how the work plays out, you still have worker 1 executing in a subroutine that is spawned by fib of 2, which is spawned by fib of 3. There could be also potentially, oh, actually, sorry. I realized I made a mistake in the slide. That P4 shouldn't be there. Sorry about that. Okay, you can ignore that P4. But the point is that in this case, P3 actually can't successfully sync fib of 3 because they're still potentially subroutine executing on a different worker, right? And so in this case, notice that a sync can be successful if there's no longer any subroutine executing on a different worker. A sync cannot be successful if there is still subroutine executing on a different worker. And so in Cilk, right, we basically, each Cilk function can itself spawn, and we support nested synchronization where a frame must wait on its outstanding child subcomputation. So in this particular case, right, what I'm showing you is the spawn subcomputation and how the execution play out, where maybe we have worker 1 executing in the subroutine, which is originally spawned by, sorry, can people see my pointer cursor?
Yes.
Okay, great. Where worker 1 is executing in this subroutine, which is originally spawned by this function, and this function itself subsequently spawns something else that's executing on worker 2. So in this case, in this particular function frame, it is waiting on 3 spawn subcomputation, whereas in this particular case, it is waiting on these 2 spawn subcomputation. And so whenever we execute sync on a particular frame, we basically need to know how many outstanding subroutines that are executing on a different worker, right? And so the question is, how does the runtime keep track of who is waiting on, who should be waiting on who? And as I mentioned earlier, actually, a function can only contain true parallel execution in its subcomputation whenever a function has been stolen. Okay, so whenever you have actual parallel execution, that's when you potentially need to check, am I ready to sync yet, right? So think back in terms of when a function, if a function never been stolen, the sync is pretty trivial, right? It doesn't need to do anything because if this particular function has never been stolen, I know there's no subcomputation that's executing on different workers, so a sync can be just a no-op. On the other hand, if this function has been stolen, that's when I have potentially true parallelism underneath this function. And that's when I need to be careful and keep track of who else is executing the subroutine. And so the runtime basically maintains a tree of what we call full frame to keep track of such additional information. Here, what I'm showing you is basically each square. You can think of each square as a full frame. The smaller square that I have the note saying spawn or call, those are the regular Cilk stack frame that we talked about, okay? But whenever a frame has been stolen, then we will create a corresponding full frame, represents both the stolen function and its corresponding subcomputation to keep track of additional bookkeeping information. And so the full frame, here what I'm showing you, sometimes a full frame, whenever it encounters a sync and the sync is not ready, then that frame needs to be suspended. And I'm showing you such corresponding suspended full frame in light blue. I'm showing you the full frame that's actively been executed by a worker using the dark blue. And so as the execution plays out and a successful steal plays out, basically the runtime as a steal, it basically promote a potential Cilk stack frame into a full frame. And each full frame corresponds to at least one function frame. Sorry, it corresponds to at least one Cilk stack frame. And we'll take a look at how that plays out. But before I go there, effectively what you can think of it is that the runtime maintains the state of the running program using a full frame tree. Okay, and each full frame has the following information, where you have a join counter that indicating the number of outstanding spawn child that's potentially executing on a different worker. It also have references to the parent and the child full frame, and then the reference into the cactus stack, or in particular references into these Cilk stack frame representing whatever the subroutine represented by the full frame. Okay, so let's take a look at how this full frame tree is maintained, right? So say here, P1 is just actively executing some full frame. And at the beginning of the execution, we always have the root frame having the full frame, because that's the beginning, the root of the computation. So a steal plays out, say in this case, say P3 steals from P1, right? Again, we are stealing from the top two frame because we want to maintain that we are resuming at the continuation of the spawn, not continuation of the call. And in this case, P3 basically steals that full frame. But we need to also create additional new full frame, right, for the victim to represent whatever subcomputation that is still executing on the victim. So in this case, we'll create a new full frame that's pointing to the rest of the computation that's executing on P1, okay? And in this case, this new full frame is basically the child of the stolen frame, right? So we create a parent-child pointer to represent that relationship. And then maybe subsequently the P3 continue to execute and resume the stolen function and creating more Cilk stack frame. P2 then subsequently steal, and say in this case it happened to steal from P3. Again, it steals the top two frame because we want to respect the fact that we are only resuming the continuation of spawn function. And again, similar thing happened, right? We create a new full frame and leave that with the subroutine that's still left on P3. And then again, we connect the full frame that we just stolen with the new full frame that we created that's left on the P3 to represent the parent-child relationship. And in this case, we know that whenever P2 say, when it resumes the stolen function, if it's encountering a sink, now we can check the full frame tree to see if there's any outstanding subroutine that's still executing on different worker. Okay, and in this case, because by looking at the full frame tree, we know that there are still subroutine, outstanding spawn subroutine that are executing on P1 and P3. We know P2 is not ready to sync yet, and so in this case, P2 has to basically suspend this particular frame. Okay, and now P2, because it's out of work to do, it goes and works steal to find more work to do. And so that's basically how the runtime system builds up the full frame tree. Now, let's think about the common case for sync, right? So today, if the application has ample parallelism, what do we expect to happen when the program execution reaches a sync? So again, a sync basically can be successful if there's no outstanding spawn child executing on a different worker. On the other hand, if it has been stolen and there are outstanding subroutine executing on a different worker, a sync can fail. And so when we reach a sync, do we typically expect the sync to succeed or sync to fail? So does somebody want to elaborate why they think it should fail? Right. Okay. So the common case is actually it's likely to succeed because for the most part, if your application has ample parallelism, there's not going to be a lot of steal. For the most part, the worker will steal something and just operate on its own local deck. And for the most part, it's going to take the regular fast pass where it mirrors the sequential execution, where you spawn something and then you return from your spawn and your parent is still on your deck where it hasn't been stolen. And so for the most part, right, it's actually going to succeed. And for most functions that you spawn, you end up having no outstanding spawn children executing on other worker, okay? And so in this case, we also want to optimize the case for when the Cilk sync is likely to succeed and not fail. And so what happens is that, again, because each full frame has references to the Cilk stack frame corresponding to the current subroutine, we basically have a flag stored in the Cilk stack frame that maintains the frame status, where the flag is only set if it's stolen, okay? And because we know only stolen spawning frame only stolen spawning frame can potentially fail on the execution of a Cilk sync. And so what we do is basically whenever a frame gets stolen, we set the flag. And whenever we execute a sync, we basically check the flag and we just don't do anything special if the flag is not set. And so roughly, when you compile Cilk sync, it corresponds to the following pseudocode. You can ignore sorry, I didn't actually get into this, but whenever a Cilk sync gets suspended, eventually somebody has to resume it, right? So again, we need to know the execution state. But basically, we use the same buffer that we use for spawn to make sure that we have the process state stored away in the event that it needs to suspend. And where we actually call the runtime and suspend the frame if today the flag is set, okay? So basically what I'm saying is in the runtime data structure, there's a flag. The flag gets set whenever you successfully steal the function. And so this code gets the Cilk RTS sync, which is a non-trivial sync, only gets invoked if the flag is set. On the other hand, if the flag is not set, then the Cilk sync doesn't actually do anything. It just translates to a no-op. Okay, so now, sorry, any questions so far? Okay. So in the last part of this lecture, I'm going to basically briefly go over some of the design choices, okay? So earlier, as we mentioned, right, the organization of the runtime abide by the work first principle, which states that we should optimize for ordinary serial execution at the expense of some additional overhead and steal. And so as we saw, basically a lot of code is organized into this principle where the compiler implements the fast pass, where fast pass include execution of function where no steal has occurred. And on the other hand, the runtime library handles the slow pass of execution when the steal actually occurs and there's like actual parallelism. Example of that including the THC protocol, the implementation of Cilk sync, and the organization of closures or the full frame tree versus Cilk stack frame, where recall the Cilk stack frame is just used to store away the execution context, whereas the closures or the full frame tree stores the full execution context necessary in order to enable actual parallel execution. And the runtime basically manages the closure, whereas the Cilk stack frame is mostly managed by the compile code. Okay. Now, I want to say something about other design choices. Okay, I didn't really focus a lot on this, but in classic randomized work stealing, we always, whenever a thief steals, it always steals from a randomly chosen victim and steal from the top of the stack. And there's a reason why we do this. We didn't get into a lot about the theory, but this random choice and the stealing from the top actually allow us to amortize the cost of the steal against the span term. And this is how we are able to obtain the time bound, the expected time bound of work divided by P plus big O of T infinity. And furthermore, actually, the randomness also avoids contention, right? So note that in the TH protocol, the thief always has to grab a lock, okay? So what that means is that at any given point, there can be at most one thief that is currently engaging in the THC protocol with the victim. Because any thief that wants to steal from a particular victim, it has to first grab the lock on the deck on victim stack. And so what we do in the runtime is that a thief will always do a try lock, meaning it attempts to grab the lock. The try lock actually doesn't block you whenever the lock is already being held by someone else. It would just return with a signal signaling that you failed to acquire the lock. And so in the runtime, a thief will always first attempt to try lock. If the try lock successfully grabs the lock, then the thief will subsequently engage in the THC protocol with the victim. On the other hand, if it fails to grab the lock, it just gives up and it tries again with a different victim. So this randomness avoids contention. There used to be an old bug in the runtime where every worker has the same random number generator initialized with the same C, which actually led to pretty high contention because everyone ended up choosing the same victim, same sequence of victim. And so this, we fixed this bug by actually ending up having the C initialized differently for every worker, and this avoids the contention. Now, in terms of this implementation of spawn, right, in classic randomized work stealing that we talked about, the worker actually does continuation stealing, which is to say that whenever we encounter a spawn, the worker go ahead and execute the spawn child. And the continuation is what gets pushed onto the deck to be available to be stolen. In the literature, people also talked about a different choice is called child stealing or held first, which is it pushes the spawn child onto the deck so that it can be stolen. Going back to implementation of spawn, in the scheme that we talked about, we always use continuation stealing, which means when you encounter a spawn statement, you go ahead and execute the spawn child, and you package up in the continuation to be stolen. Now, in the literature, there is an alternative being proposed called child stealing, which is to say, when you encounter a spawn, you actually package up the spawn function and then push that onto the deck so that the spawn child can be stolen. Now, so in this case, then what you do, say in this example, you would actually package up bar and then go ahead and execute BAS. And then when you encounter the Cilk sync, then if bar has not been stolen, you pop it off and you execute bar. Now, the problem with child stealing, so in Cilk, we basically choose to do continuation stealing. Why? Because in child stealing, you can potentially encounter a problem with space. Just imagine if a user write the following code where you are going around the loop 1,000 times, and then for each index I in the loop, you spawn off a subcomputation. In the case of child stealing, you are actually going to create 1,000 work item or however many iterations that you're doing and push them onto the deck before you actually start doing any useful work. Right? On the other hand, for continuation stealing, what you would do is you will work on the spawn iteration and let the rest of the loop packaged up as a continuation that can potentially be stolen. Right, so in terms of continuation and child stealing, just comparing side by side, continuation stealing potentially provide better space utilization It has better work efficiency because instead of spending time packaging up the spawn child, you just go ahead and execute. And the one worker execution furthermore follows the serial execution, whereas in the case of child stealing, the one worker execution does not necessarily follow that of the serial execution. And as a side note, which we didn't really talk a lot on, but with continuation stealing, you can actually bound the number of cache misses during parallel execution, and there's such result in the literature, whereas for child stealing, there's no proven bound. Okay, so I just want to end. For runtime implementation, I always advocate for continuation stealing and not child stealing. So this is like a picture of me wearing a t-shirt that says "Only monsters steal child." All right, this is the end of my lecture, and I will now take questions.